Hello and welcome back to another adventure of Risc-V emulation in a high-level language. So far, we've been working a lot on building the assembler for the Risc-V assembly language. And at this point, it's as complete as we really need it to be. There are several more Risc-V instructions that we could add to the assembler, but they're not really necessary for the work moving forward. Instead, I'd like to try to change the focus over to the emulating side of things, because that's the direction I want to head. And as I was reviewing the code, I realized that the memory interface is not really up to par. So I'd like to spend some time refactoring it a little bit and maybe adding a few more features to make it a little bit better than what we have today. So let's take a look at the memory class real quick and see what it does today. So when when you create a memory object, or the instance of the memory class, you pass in a linear array of bytes, and then we hang on to that array of bytes, and then we have various methods to retrieve the different bytes. And this is fine, but there is a few problems with this approach, and that is what we're addressing in this episode. The first one is, if you don't know ahead of time what memory you're going to be using, then you're pretty much stuck. There's no way to add more ranges of bytes to the memory object. This becomes important, for instance, if you wanted to implement something like a dynamic memory allocator, which is very common. Another flaw is that there's no way for us to indicate whether or not the memory in question is readable or writable. So I cannot, in the existing design, prevent writes from happening to memory that has been marked as read-only. So we need to implement that in order to, well, emulate the typical kinds of memory that we have on modern CPUs. So what we're going to do is we're going to add a few methods to memory, and we're also going to remove this constructor so that you explicitly have to request the memory that you wish to allocate. All right, so let's get started. So I'll start by writing a few memory tests, and we need to sort of bear in mind that the unit tests should be guiding us when we're designing this so that we don't break existing code. Unfortunately, the only unit test that we did have before has been commented out. So in essence, we have no tests to begin with. So I guess we'll get started. Let's uncomment this code and see whether it can still compile. And it looks like it doesn't. Okay, so what does this test do? Well, it says create a chunk of memory and then create a memory object, a memory manager, and then create a chunk of memory at the address 0 and of length 42. And what we're verifying is to make sure that the memory that we did allocate has the address 0, and then we make sure that, all right, okay, so I see what this code is doing. It's basically making sure that, well, let's take a step back. Allocation, this memory allocator allocates memory in chunks of bytes per page, where bytes per page is an undefined constant, but typically this is the page size, which is defined by the processor. Typical size for this is 4096 bytes. So let's just go to the memory class and let's see, why are we not picking up the memory object? Or maybe we need to build the project. Let's try that. So let's build. All right, and now, okay, it's completed because there is no constructor with 0 arguments. So let's just create them. So this one is a new future one, and let's mark this one as obsolete, and we'll be migrating over to this one in the future. Okay, so let's add a public constant, and let's call it, it's an unsigned integer, and it's going to be bytes per page. And let's make that 4096. So the intent now is that if you allocate a number that's smaller than 4096, then the the memory class will round that up to the largest or to the smallest multiple of 4096 that's still bigger than say a number like 42. So if I allocate 42 bytes, then I should get an allocation that contains 4096 bytes. And that's what this test is making sure, is that it's testing to make sure that we can read the last byte of that memory range. So if I take the address that was allocated and I add the size of page -1, that's the address of the last byte of that page, and that should be valid. But then if I then try to access the byte beyond that, then that should be a failure. Okay, great. So we also need a method called allocate, and so that will tell me where I wish to allocate the page. And this looks like if you say 0, that means you're telling the memory subsystem, please allocate this anywhere you want. And then 42 is the size. So that is the number that we want to round up to an even multiple of bytes per page. Okay, right. So that's that. But we also want to say that this memory should be readable or writable. We want to specify the access flag. So let's create an access mode enumeration, and and it looks like the Rieko project, which we are linked with, actually has one of those. Let's create our own though. Let's create our own. So we'll create our own enumeration called access mode, and we'll add it here. And it's an enum. So public enum access mode, and it's a flag collection, so we'll mark it as a flags collection. And then we have to define flags for read, which traditionally is 4, and write, which traditionally is 2, and then execute, which is 1 traditionally. And then let's write a few combinations. So read write memory would be read or write, and read write and execute is read or write or execute. Those are also read and execute is read or execute. All right, so we have some commonly used combinations that we'll be using. All right, let's go back now to our memory test. So now what I want to say is I want this to be read-only memory. Let's start with that for fun. All right, so let's jump in and build this method. So we have to generate a method called allocate. So what should happen here? So this would be the address, and let's make that an unsigned integer. Address. And let's make the size also an unsigned integer, because the sizes can never be negative. Right, or byte size maybe, like this. All right, and then the access mode is the mode of the memory. All right, so what do? Well, first of all, we need to check our parameters. So if the byte size is 0, then we're not allocating any memory. That's probably an error. So we'll check to see if byte size is equal to 0, then we throw a new argument exception like that. Okay, so now we're happy that the size is appropriate. So what we want to do now is check to see the address. If the address is actually, we could consider somebody would want to allocate at the address 0. So let's have a magic flag. We'll introduce a flag that says public const uint anywhere, and that is going to be this magic number, which is the all ones size 200 uint, so 32 bits of ones. It's a very special address, and if that address is being requested, then we can allocate this address anywhere we want. Otherwise, if it's not that address, then we allocate the memory at the specific address. So we'll check to see. If address is equal to anywhere, then, And we haven't implemented this yet, so we'll throw an exception just to keep that as a marker. Otherwise, we will allocate a chunk of memory. So what do we do? Well, all of these chunks of memory that we're going to be allocating need to be tracked. We have to have a place where we keep track of where those chunks of memory are. And I'm going to use a sorted list for this purpose. Now, some of you might instantly react and say, well, wait a minute, isn't that going to be extremely slow? And the answer is yes, it is going to be very slow. But again, this emulator is not a one that is going to be competing in an arena of speedy emulators. It's instructional. And so here we're going to make the simplest tools to build this emulator. And of course, if you want to speed this up, there are various ways that you could speed this up. But we're not going to do that now. We're going to focus on making the code understandable. But it is very similar to what the operating system like Windows or Linux do when you ask them to allocate memory. They have to keep a data structure internally that keeps track of where all the memory and all the data is located. And so that's what we're doing here. But we're doing it in a very convenient and simple way. We are not we're not going to be focusing on performance at this stage. So the sorted list is a dictionary data structure, and what it will map is an address, which is going to be the beginning of a memory block, to uh, to a chunk of data, which is going to be some information about this particular chunk of memory. Now, why a sorted list? Well, it turns out that it's convenient to use sorted lists because then, if you have a memory access that isn't exactly at the beginning of a page, we can ask we can ask a sorted list. Can you find the page that is on that address or below that address? So, sort of the least the, the highest least upper bound. And I'll show what that looks like in just a few secs. So let's create this dictionary then. So it's a private, read-only, sorted list. And it takes a uint, which is the address of the base of the memory area. And then we have a memory descriptor, maybe? Let's call it a memory descriptor. And these are memory, well, let's just call it descriptors. Great. So in our constructor, we will create this dot descriptors equals new, or we can even use this clever new syntax that Microsoft introduced. All right, great. And then we're going to stop using bytes, but I don't want to remove it quite yet. So we'll just we'll leave it in for now, but we are going to have to remove this at some point. So I'll just put a comment here to do replace with usages of descriptors. Okay, so this memory allocator, which allocates a chunk of bytes, it always assumes that the memory address at which these bytes are allocated is address 0. So I'm just going to follow this by, actually, we'll do this. We'll call the other constructor. And then after that call returns, we now tell it to allocate a buffer. And now this gets tricky. No, let's back off from this. Let me come back to that. It does get tricky. But anyway, so here we have our descriptor. So now we need to define what is a memory descriptor. So memory descriptor is a, I can probably make it internal because nobody else should be looking at this. I'll make it inside here. It's an internal class. Might even make it private. So a memory descriptor contains a uint, which is the address of the memory in question. It will also contain an access mode, which describes the access mode of this particular field or chunk of memory, and then the actual bytes themselves. So something like this. There. Okay, so that is a memory descriptor. And let's make a constructor for this. So this is a memory descriptor taking a uint address, an access mode, and some bytes. And then we just assign these fields. So this dot address equals address, this dot mode equals mode, this dot bytes equals bytes. Okay. So when we call allocate, we need to create a memory descriptor, and we need to create a chunk of memory, and then store all those things. So let's do that. We'll say var, oops, caps lock is on, so var descriptor equals new memory descriptor, and we pass in the address. Oh, we forgot the size. I need to fix that. Right, so let's we need to pass in the address and the size, and then the mode, and then some bytes, which you haven't allocated yet. But before we do this, remember that I was saying we want to round up the memory to an even page size. That is, we want to round up the bytes that we're allocating so that the actual number of bytes that we allocate is always a multiple of bytes per page. And the way to do that is to do a little computation that occurs very frequently in these kinds of circumstances. It's called alignment. So what we'll do is we'll create a new method called align up, which will take a number, which is the address, or number, let's just call it n, and then the alignment amount. So this is the number that we want the result to be a multiple of. So this will be uint unit size. Let's call it that. So how do we do this? Well, again, we're focusing on transparency and ease of understanding here. This can be done a lot more cleverly if we know, for instance, that the unit size is an even power of 2. But for now, we're going to do this. We're going to say, take the number and then add to that number unit size minus 1. All right? And then we divide this by unit size. So let's take a look and see what this happens. So if n is equal to 1, say, then n plus unit size minus 1 will become unit size. And if we divide that by unit size, we get the number 1. So this would allocate 1 page. And then finally, at the end of all this, we then want to multiply it all by unit size. So I hope that is clear. Let's take another example. Suppose that the unit size is 4095, which is 1 byte less than a page. Then if I take 4095 and I add another, well, even better, let's take a full page size. So n is 4096. So we take 4096 and we add 4096 minus 1, which is 8191. But if you divide that using the integer division, because these are unsigned integers, we're going to be using integer division, then if you divide that number 8191 by the unit size of 4096, then that's going to get rounded down to 1. So we get exactly 1 times the unit size becomes 4096. So the numbers between 1 and 4096 all get rounded up to 4096, which is what we wanted. But if I specify 4097, then 4097 plus unit size minus 1, 4095, that gets turned into 8192. And if you divide that by unit size of 4096, then you get 2 units times the unit size, so ending up with 2 pages. So this will round up any number that is is more than an exact multiple to the next page multiple. So this will guarantee that if I allocate a number, there will always be enough pages to store that many bytes. So let's return this result to the caller. And now when we allocate the memory, we will round up the memory. So we'll say byte size equals align up, byte size bytes per page, like that. So now we have aligned up, so we have made sure there's space for the memory, and then we create a descriptor, and then we put it in our table. Now you may be thinking, well, what if there's some memory already at that location? And we'll get to there. We'll have to write a unit test first before we write that logic. So first, we're just going to blindly assume that this is a free memory area. So we'll just create descriptor, and then we will descriptors, and then add this at the location address. Oh, no, descriptor. Good. All right, so at the end, then, what we want to do is return not an object, but the address at which this memory was located. So let's do that. We'll return the address at which this was located. Right, so if everything went well, we should be able to run our unit test to make sure that this works. So let's see if it passes. Oh, we have a build problem. Let's check that out. Oh, it's just a warning. We're going to ignore that. No, we do have more. Oh, these are warnings. Okay, yeah, we added an obsolete marker. So we're running our unit tests, and there's a failure. All right, so let's take a look at the failure. Why are you so unhappy? We have a null reference pointer, and that's because we haven't updated all of our code. Right, so is valid address now needs to change, because now it needs to look in the descriptors table and find and perform its validity test that way. So let's fix this. Let's get rid of this. All right, so this is now no longer a sufficient test. We have to look the field up inside of the descriptors table. So what we'll do is we'll say, let's try to find this page, try get lower bound. Then we pass in the IPTR, which really should be called address, but all right. So if we cannot find a page that's located below or equal to this address, then we're surely invalid, so we'll return false. But if that returns true, then we have two cases we need to consider. The first one is that the address is actually inside of that memory. The other one is that the address is actually beyond that memory. So we'll need to add a method to the descriptor that says return descriptor is inside, and we pass in the address that we're testing. And then is inside will look something like this. We'll take what code we had, so we'll compute the difference between the address that is being probed and the base address of this descriptor. So we'll say, let's call this address. Actually, let's call this. No, let's use the word address. Address, and then we'll say var IPTR. We'll rename this shortly. Is going to be the address that we were given minus the base address. So what's the base address? The base address is this dot address. Okay, let's rename this now to offset. So this is a non-negative number. So it could be 0 or it could be bigger, but it will never be smaller because it's unsigned. So our check, all it has to do is to check to make sure that the offset is less than the byte length. And that's it. All right, let's run our unit test to verify that that works. All right, still failing. So what's the... we're still using this dot bytes. Wait a minute. Oh, that's interesting. Let's put a breakpoint here and look at what's going on. Bytes should be initialized, so I'm a little confused as to why it wouldn't be initialized. Bytes, well, look at that, bytes is null. All right, so that means that somebody called us, okay, I know why. So let's go back to our, the place where we create these beasts. We weren't fully done with it. We have to also initialize the bytes. So when we find the method allocate, it's using the this.bytes, but we need to create a local variable called bytes. And we are going to, oh, my keyboard is acting up here. Not sure what's going on. There we go. So bytes is going to be a new array of bytes of this up-rounded byte size. And that is now a local variable that gets fed in there. All right, that should work better. Let's try running our test. Let's see if that works better this time. And we have a green light. So that means that we were able to allocate a chunk of memory at a particular given address. So now what we can do is go back to our constructor that we have here, and here, this is the old, this new constructor now, the old constructor we now want to change so that after calling this, we now allocate an area of memory at the given address 0. And instead of giving a byte size, though, we're going to give it the actual bytes that we want to place there. So this is sort of we're being given a bunch of bytes, and we're going to put them at that address. And we don't know what the access mode is, so we're going to give it a very generous access mode, a very dangerous one, the read, write, execute. For our emulator, it's not that critical, but in a real environment, this is a very dangerous access mode because it allows you to both read and write and execute the bytes in that memory area, and that could lead to security issues. I'm not going to delve into that deeper, but it is a dangerous alternative. Okay, so what we'll do here is we'll create another, we'll create an overload. We're going to call it public uint allocate, and we say address, but here we'll pass in an array of bytes, and then the access mode. Okay, so in this case, we will do it like this. And then bytes need to be converted to a uint. And then here we allocate the chunk of memory, and then we return the address. Actually, we return the allocate address, bytes, and mode. Nice. Okay. Let's make sure that our unit test still passes. Nope, it is failing. And did we make a mistake? Let's put a breakpoint here and take a look at our refactored code. Let's run that in the debugger. All right, so that should be a valid address. The offset is 4095. The number of bytes is 42. Oh, we forgot to round it. All right, let's fix that. Where do we have allocate? There. Yeah, we need a round up, so we need to say byte size equals a line up, byte size, and then bytes per page. Good. So now, yeah, this, I'm not sure. We're passing in the byte size there. Not sure if we're actually using it or not. All right. Well, let's leave it like that for now. We may need to go back and change it later. So now this default constructor, we know, well, now we need to start working on getting rid of bytes. But before we do that, I did notice that there was another error in one of our emulator tests. Oh, there's several. Okay, they are unhappy because, well, let's run all of our tests now that we fixed that issue. Maybe it will clear those up as well. Yeah, good. Green bar. So now the next step is to get rid of the bytes member inside of memory and only use these descriptors. So what we're going to do, what we're going to do is we're going to add a new method called access. And what it will do is every time in all the places here where we are writing or reading to memory, what we want to do is also pass in an access flag that says what kind of access we are trying to do, and then we have to determine based on the address, first of all, which page is being referred to, and then whether or not that kind of access is acceptable. So let's add a method called access page. Let's put that right after allocate. And what it will do is it's a private method, and it will return a pair. It will do this. Let's start with the input parameter. So access page. I want to access a page. I will pass in an address, and I will pass in the access mode that I wish to access the page with. So what we do now is we look up the access in the descriptor. So we'll say if uh, descriptors try get lower bound address out var descriptor. If that is false, then there is no memory at that address, so we throw an exception. And for now, I'll throw an invalid operation. But we could, if we wanted to be hardcore about this, we might wish to create a new class of memory exceptions with this particular one being handled with that exception. I'm not going to do that here. I'm just going to leave it as an invalid operation. So if you try to grab something that's out of bounds, then we fail. Otherwise, what we want to do is take the page that we got and see whether the address that we wish to access is in range. And so what we'll do is we'll compute an offset. We'll say offset equals descriptor dot address, and then subtract the address we want from that address. That gives us the offset, and of course the offset has to be on inside the byte array. But also we need to check to make sure that we have access rights to that page. So we'll check to see whether the mode that is being requested is um, if the mode of request is actually on that page. If it's not, then it's going to fail. Let's see, what do we do? We will want to, and let's see, yeah, let's do this. We will use the flags capability of the flags of the access mode. So we'll say if the mode that we're requesting and the descriptors dot mode, if these don't, if the bits that we're requesting are not actually present on the descriptor, then we cannot support this operation. So this is an access denied. We cannot access the page because the page mode, or the mode that we want to access the page with, is not supported by that page. But if it is, then we calculate the offset into that page, and then we say if we're inside the page. So if the offset is larger than or equal to the descriptor's length, or the byte chunk length, then we're going to be outside, and that's also a failure. All right, so that is done. If all of those tests pass, we should have a valid page. So what we want to return to our caller now, that is going to be the offset that we computed, which is going to be the offset within the page, and then the page itself, or the page data, I should say. And this should be a uint. Okay, so now we return just that. Okay, so now this is how we access a page. We give it an address and a mode that we wish to use. We try to look it up. If that fails, we die. If the page that we got, or the chunk of memory that we got, has an access mode that isn't supporting the mode that we want or wish, then we also throw. Otherwise, we compute the offset within the chunk of memory at that address, and then if that offset is out of bounds, we also throw an exception. Finally, if all of those tests pass, then we have an offset into a page and the bytes of that page. Now, what we've written here is actually what happens inside of a real CPU, except of course this is implemented using silicon and is a lot faster than the code that we're writing here. But again, we're aiming not for and not for performance. In this emulator, we're aiming for you know ease of understanding. So now that we have this method access page, we can now start replacing all the places where we're accessing memory with this. So we'll remove now this member variable, and we'll get a lot of errors because we need to replace them with this new access that I've been talking about. So let's get rid of this. And here, instead of access, we're going to have to say var offset bytes equals access page. And here we'll pass in the address. And what are we trying to do? We're trying to read. So the access mode is going to be read. Nice. And then instead of address, we'll say offset. Good. And now we're going to copy this because it's going to be used pretty much everywhere. So here and here. And there's no longer a this bytes. We'll clean that up later. Now write, when we're writing, we have to change the access flag to write. And then do the same thing. We have another write bytes. All right. So then we have to replace all the this.bytes with just simple bytes, except for that one, of course. So we need to skip this one. That one gets replaced. That one, that one. Okay. And this. Still have two more errors. Why are we unhappy? Okay. So let's call this bytes to write. And then this needs to be cast to an integer. Get span. Let's see, where do we call get span? We're calling in the OS emulator. Let's specify the access mode we want. How about that? So access mode write. And let's go back to get span. We'll add access mode. And then we should have a few we still have an error. That's okay. Let's build the project, see if we find any more errors. That get span lost the or got a new parameter, so we should get compiler errors. We don't. Interesting. Oh, there it is. My computer's really slow. Okay, so here we're doing a disassembly, so we're going to be reading the memory. All right. That should do the trick. Let's build. Well, I guess we can remove this now. And let's run our unit tests to make sure that our refactoring did the right thing. Run all the tests. It looks like all the tests are passing. That's really good news. I'm going to take a quick commit. So let's commit the changes that we have. So what we've done here is we've uh, refactored the memory class to, what do we do? So we added access mode capability to the memory class, added support for allocation of memory from the areas. Good. Right, so now that we've done that, now we need to go back to the code and add another unit test where we try to allocate two chunks that are overlapping, because that is not supposed to be permitted. So let's go back to the memory tests and let's add another unit test where we test for exactly that. So we're going to disallow overlap allocation. So we create a chunk of memory, or well, the memory. Hey. And then what we're doing is we're going to allocate one chunk, chunk one. That's going to be at address this, I suppose. And let's make it 4096 bytes. No, 4097 bytes. That'll be exactly 1 byte more than memory bytes per page. In fact, let's just use that constant. Memory bytes per page plus 1. So this occupies 2 pages now at address 1000 hex. And then we're going to try and allocate another chunk at address 01200. And oh, we forgot to mention what the access mode is. So the access mode is again just an arbitrary one. And so let's allocate it over here. And this guy doesn't need to be as big. We'll just allocate 42 bytes. Doesn't matter. Access mode read. And this should throw an exception. If it doesn't, then our code is broken, because that means that we created two overlapping memory areas, and that is disallowed. Otherwise, we catch an exception, and we want it to be an invalid operation exception. And then we're good. So if this allocation succeeds, then we'll call assert fail and fail the unit test. Otherwise, if it throws an exception, we end up in the happy path. So if we run this unit test now, my expectation is that it should fail because it's not correct. So let's build our project and then run our test. And we might as well navigate over to the memory class and look at the allocator and see. So if this now gets executed, we're expecting it to fail. And indeed it does. So it didn't throw an exception, which means that we need to fix our code. So let's go back to our memory and fix the code. So when we determine the end, so the byte size of this object, we will have to first check to see whether there already is a descriptor at that address. So we have to go and ask the descriptors, is there somebody at that address? And then the address is out. Let's give it a different name. So if there is an existing descriptor, and we know, well, we want to make sure that we are the lower bound. So if there exists a descriptor and that descriptor is such that it would overlap with the allocation that we are about to make, then we need to throw an exception. So if descriptor existing dot address plus its last byte, or the address of the address beyond the last byte, if that address is larger than the address that we're trying to allocate, then we have a problem. Oh, invalid. And let's write a message here. Memory areas would overlap. Okay. And we need to balance our parentheses like so. If we run the unit test now, then we have a green bar. Beautiful. Next thing we want to do is to make it possible to allocate a memory at some random address. So what we'll do is we'll say mem allocate any address. So recall that we added this constant anywhere to the memory class, which indicates that we want to allocate a chunk of memory anywhere in the address space. We don't really care where. So we just need to take care to make sure that we're not overlapping with any other memory area. So what we'll do is we will do a first fit allocation. That is, we'll sweep through all of the chunks in the descriptors that we have to try to find an available address. And I'll show what I mean by that. So first of all, we need to check the base case, which is when there's never been anything allocated. So I have a memory, and I just allocate something at some address. So we'll have, and we will say mem allocate, and we'll allocate an address at address anywhere, so memory.anywhere, and we want it to allocate 42 bytes or whatever, and the access mode, let's try a different one just for fun. Okay, so now we have a chunk of memory, and we can hope that that address is not 0. So that's one of the things we want to verify, that assert that the address is not equal to 0, because we want to use the address 0 as the 0 page, which on most environments indicates that, well, we reserve the page at address 0 so that we can catch uninitialized null pointers. So we'll say that if they are not equal, then we want to basically make sure that the address is not equal to 0. It could be anywhere, but at least it's not at 0. So that's something we want to check. And then we want to write another unit test that says, if I allocate one chunk of memory, so the first one will be allocated someplace, and then we'll create another allocation, and that could be anywhere as well. And we just need to make sure that adder, oh, this is very trivial. Let's just have a condition that we expect that if we do this in a completely blank memory, then we want adder 2 to have a higher address than adder. That's about all that we can guarantee. Great. So we create a memory, we allocate 2 chunks of memory, and we just make sure that the second chunk of memory is located at a higher address. So let's go ahead and we'll run all of our unit tests, and of course we know that they will fail, but while that is running, because my machine seems to be very slow right now, I'll start coding on the actual implementation. So what do we do? So this then is where do we go? We want to go to allocate here. So allocate, in this case, if address is anywhere, yeah, and we're hitting this exception now because we haven't implemented it. So if the address is anywhere, we'll start at a valid address. Let's say we'll assign to address the address that we, since the caller gave us anywhere, we're now going to reinitialize to some given address. We'll use the address of page bytes per page. Notice that that is not going to be 0, so we'll start at some non-zero address, and then what we'll do is we'll loop through all of the existing memory allocations to see whether we can allocate someplace if there's a gap that is available. So we'll say for each var descriptor in descriptors. So we'll check to see whether there's a gap, an appropriately sized gap below this descriptor. So we'll start at the descriptor, its address, and then we'll subtract from that the address that we're hoping to allocate. Let's turn that into a signed number because we want to check that, make sure that this is not negative. So this is going to be the gap between the address, the descriptor that we just found, and the next available address. And since this sorted list is in sorted order, this means that this loop is going to be incrementally attempting to allocate at higher and higher addresses. All right, so let's see if we can find a gap. So if this number is, in fact, we want to do this. We want to add the address. We also want to subtract the length of the memory. Right. So this is the address of the top, or the first address beyond the end of our chunk of memory that we would wish to allocate at address. If that number is bigger than the descriptor address, let's do that. You know what? Let's make a function out of this. So we'll create a new method called find available address. Let's do that. And we'll pass in the bytes that we want. In fact, we only need their length, so we'll just convert that. Call it a gap. And that will return the address where we can allocate. Good. So the uint is the bytes.length. And then that method is going to be this. And so this function will guarantee that if it returns, then the address that we have is an address that is valid and is big enough to accommodate the chunk of memory that we want. And then we know that it's big enough, so we'll add this code here. Like that. So now all we need to do now is, I'll copy this as well, I suppose. Now you need to implement find available address gap. So again, we'll start with an address that we want, and it's going to be starting at the bytes per page. That's our minimum starting address, and then we do a for each of our descriptor in this dot descriptors, and we say if the address that I am asking for plus the length of the memory that I'm asking for, if that is bigger than the descriptors address, then I'm overlapping with it. So I have to continue. But if it is less than or equal to, what do we call this? Hold on a second. Oh, right, we need the I'm iterating over the entries of the dictionary. I just want the values of the dictionary. There we go. All right. So if we fit inside the gap, then we return the address. This is great. We're happy. Otherwise, we need to set up the next address that we're trying, and that address is going to be the address located at the end of this current descriptor. So we'll say address equals descriptor dot address plus descriptor dot bytes dot length. Nice. So we'll loop through here, attempting to find an address. But if all of those attempts fail, then address will have an address which is beyond, well, it's either going to be bytes per page in the case when there are 0 pages in the memory, or if there are pages in the memory, it will have an address which is beyond the last page that we allocated. So now we can just return that value. There are some boundary conditions here, of course. What happens if all of the available address space is consumed? We're not going to worry about that for now. But this function could probably be made a little bit more robust. But again, we haven't written the unit test for it, so we're not going to write code that we don't have unit tests for yet. So now we build. We are expecting this now to work. And this machine is very slow. But all the unit tests pass. So we have now refactored our code. We haven't changed the main interface of the memory class. All the classes that were using it before are unaware of the changes, but now what we've done is we've implemented the capability of allocating multiple areas of memory. One thing we haven't done though is made sure that when we execute code, we are actually reading the memory as executable. So we need to validate that. So let's go back to our emulator, and actually the emulator class is over here. Let's see how it reads bytes from memory. So it has this the exec code does an is valid check before it actually reads the instructions. What if we had a way to say let's add a method called isAccessible where we do the same check, but we also pass in a mode that we wish to the page to be in. So instead of isValidAddress, I will have while the memory, let's see, I'll call it isAccessible. How about that? And then I pass in the access mode dot read and execute. So if the memory is not readable or executable, then this will throw an exception. And before I write this, we will probably, well, we're going to run into some, we're going to run into some issues because the memory that no, we're not. We need to write a unit test for this. So let's write a unit test. Let's modify one of our existing unit tests to make sure that the memory that it creates is the setup here is always going to create an appropriately. Let's see, what could we do? Let's see, the run test method. It always creates a memory with readable and writable and executable memory. So let's change, or let's add another one where we overwrite the memory. We'll create a, let's grab all those. Let's create a new test called disallow execution if not executable. Let's do it like that. Nice. So we're going to grab all those member variables and we're going to run a test where we create an assembler and we try to execute some simple instruction, run test, and we'll pass in. What we'll do, we'll do the add-I. This is basically a no-op, so we'll just execute the no-op, and this should throw an exception now because we are expecting the emulator to right. So here's the critical change. The memory that we create, we're going to say this dot memory dot allocate at address 0 chunk of bytes, but it is read only, so it's not like that. And this should throw an exception. So we'll wrap it with a try catch. And then we say assert fail if that was successfully executed and the catch is invalid operation exception. Okay. Let's So let's try that. I'm expecting this to fail. And of course, we haven't implemented the new method, so let's let's go back to that. It is accessible. So is valid address has a new cousin. It's called is accessible. So we do the same thing here, but not only we have to check inside, we also have to make sure that the access mode that we're the requested mode and the available access mode yield requested mode. Right? Let's run our tests. And I apologize for the slow build time. I think this this computer that I'm running on is being heavily loaded by the streaming software, so it's having a hard time keeping up. All right, so our changes are successful. Great. So what we now have is a revamped memory model, which looks a lot more like a um, typical CPU, a modern CPU with multiple memory areas that can be given different access modes. So I'm going to wrap up work here, but in the next session, what we're going to do is using this new facility to allocate a separate stack area and a program area for our program so that our executable program doesn't stomp on the stack or we don't stomp on our executable code during execution. So until then, thanks for watching, and we'll see you next time.